In this lesson, we're going to talk about equipotential lines, and here are your objectives. Remember that potential is equal to the electric potential energy per unit charge, that it's a scalar, and also remember that we can think of potential as being analogous to height. You've probably seen topographical maps that look like this of landscapes where all points at the same height are connected by contour lines. They're a way of showing you the terrain. So this is a topographical map connecting all points of the same height on these contour lines. Let's consider this line here. So if you were to walk around this line here, you'd be staying at the same height, and so your gravitational potential energy wouldn't be changing. Now, if you consider a point on there, let's imagine a 1 kilogram mass sitting at that point, or a 2 kilogram mass sitting at that point. Because they're at the same point, obviously they have the same height. The 1 kilogram mass has less gravitational potential energy than the 2 kilogram mass does, but if you consider their potential energy per kilogram, they have the same. The 2 kilogram mass has twice as much gravitational potential energy as the 1 kilogram mass does, but it's got twice as much mass. So its potential energy per kilogram is the same in either case. So if you think about it that way, the heights shown on this contour map are expressing potential energy per kilogram. And remember that potential is equal to potential energy per unit charge, or per coulomb, and that potential and height are analogous to each other. So we can do the same kind of thing with potential. We can draw these kinds of topographical maps. So equipotential lines connect points in space at the same potential. Let me show you a couple of examples of what I mean. Here's a parallel plate capacitor. We'll make this side negative, and we'll make the left side positive. Let's first draw the electric field lines. Remember that the electric field lines are going to point the direction that a positive charge would experience a force, and so they're going to point in this direction. Also remember that the electric field of a parallel plate capacitor is uniform, and so these need to be equally spaced out because the spacing shows the electric field strength. So those are my electric field lines. What about the potential and the equipotential lines? Well, let's say that this was 0 volts and this was 40 volts. We've got a 40 volt potential difference between our two plates. If we were to measure the potential at different points in space between these two, we would find that at any point along this line, for example, we'd have a potential of 10 volts, or 10 joules for every coulomb of charge. Over here, 20 volts. And over here, 30 volts. So we've got these equally spaced lines that are perpendicular to our field lines, and these are equipotential lines. All points along this blue line are at the same potential, 10 volts, relative to 0 over here. All points along here are at 20, etc., etc. Think of this again as analogous to the height situation. Think of the negative plate as being the ground and the positive plate as being higher up in the air. As you move upwards off the ground to higher and higher heights, you're getting to higher potential energies for whatever mass you are moving upwards. So the potential energy per kilogram is increasing linearly as you move up off the ground. Similarly, in the parallel plate situation, as you move a positive charge to the left from the negative plate towards the positive plate, you are getting more and more potential energy stored in that positive charge, and that potential energy per unit charge, or per coulomb, is increasing linearly as you go to the left. And that's why we have these equally spaced equipotential lines. Again, the equipotential lines are perpendicular to the field lines, and in the parallel plate capacitor setup, they are equally spaced. Now let's look at the equipotential lines around a positive charge. So first let's draw the field lines. Remember that the field lines are going to radiate outwards, and for a positive charge, they're going to point outwards as well. So these are our field lines. So we've said that in the previous case, the equipotential lines run perpendicular to the field lines, and that actually holds true always. So the equipotential lines are going to form concentric circles, because that's the only way that they can be perpendicular to all the field lines, and they're going to get more spaced out from each other as we go outwards. So they start off closer together, and then they get further and further spaced out as we go. So then the next one might be out here, for example. Okay, so concentric circles getting further and further spaced out. And just to make up some numbers, this one might be at 40 volts. If this is a positive charge, we would go down in potential as we go away. So this one would be at 30 volts, 20 volts, let's say, and 10 volts. And when I'm talking about the spacing here being equally spaced and here getting more spaced out as we go, I mean the spacing in equal increments. So here I'm using 10 volt increments. Here a 10 volt increment is going to get farther and farther away from each other, and here the distance between each 10 volt increment is the same. So in both cases, the equipotential lines run perpendicular to field lines, and that's always the case. So equipotential lines are always perpendicular to field lines. And if we think about the work required to move along an equipotential line, so along here, let's say I have a charge there and I want to move it to there. If I think about that in terms of the height analogy, that's like saying I have a mass here and I want to move it over to here. That's not changing the gravitational potential energy of that mass at all, and so this requires no work. In the same way, moving here from A to B would require no work either. So it takes no work to move a charge along an equipotential line. I could go from A over here to B over there, and because I'm not changing the electric potential energy and I'm not changing the kinetic energy either, if I'm doing this at constant velocity, I'm not changing the energy at all, it takes no work. So equipotential lines are always perpendicular to field lines, and it takes no work to move a charge along an equipotential line. That's an introduction to equipotential lines.